Hello students, and welcome to Topic 5 of Alternative and Renewable Energy Sources. This topic we will be covering solar photovoltaic systems and components. This topic's lecture is broken into two parts. In each part we will do an activity. The activity is recorded and you are to work the activity along with the recording. This gives us the various components of the solar PV system. We of course have the PV module. PV modules generate DC or direct current. In almost all cases, this direct current must be converted to alternating current. The inverter is what changes this DC current to alternating current. On standalone systems, this is not connected to the grid. A means of energy storage must be provided. The most common type of storage is a lead-acid battery. A specific piece of equipment must be provided to charge the battery, protect the battery from overcharging, and protect the battery from over-discharging. It is called a charge controller. Some systems, especially off-grid systems, may have other sources to provide energy, such as generators. Then, there is what is called a balance of systems, which includes the wiring, the overcurrent protection, and the surge protection, and the disconnect devices. Here's an example of a standalone system. These are usually in locations where the grid is unavailable. These systems, standalone, must provide all the electricity for that building. To keep these systems from becoming too large, these buildings are usually made very efficient. The most popular type of system is a grid-connected system. These systems usually do not have storage capabilities and are connected directly to the grid. These are usually net-metered systems. When the system is producing more electricity than the building is using, the extra electricity is added to the electric grid. When the system is not producing enough electricity to meet the demands of the building, the extra electricity is drawn from the electric grid. Here is a more complete list of solar PV system components. Again, we have the panels or modules, the charge controller, if it is a standalone or grid-connected system with battery backup, the inverter, and the balance of the system. Strict terminology is given here. The solar cells are combined together to form a module. Modules are assembled together to form a panel, and panels are assembled together to form an array. Sometimes the terms module and panel are used interchangeably. Here we see an open view of a combiner box. An array may have many individual circuits. These circuits are run into the combiner box and combined into one circuit that goes to either the charge controller or the inverter. The combiner boxes usually have a circuit breaker for each of the individual circuits coming into it. Here there are 8 PV modules, with 2 of them being wired together to form 4 individual circuits going into the combiner box. There is only one circuit leaving the combiner box and going to the charge controller. The charge controller is connected to the batteries. The charge controller is connected to the inverter through a DC disconnect. The inverter is then tied to the main panel box or breaker box, also through a disconnect. This slide gives us an excellent view of 5 circuits coming into the combiner box from their array and 1 circuit coming out and going to the charge controller or inverter. It is a function of the charge controller to keep the batteries from being overcharged or over-discharged. The most common type of battery used for storage in the solar PV system is a lead-acid battery. These are not common batteries as used in the automobile. These are especially deep cell batteries, which are made to be deeply discharged and charged for many cycles. A standard automobile battery would not last under the conditions of a solar PV system. This is an example of a battery bank and assembly of a number of batteries. The inverter changes the direct current coming from the solar PV array into alternating current. The one shown here is for a grid-connected system. This inverter synchronizes the electricity from the grid so that it matches the same voltage and cycles. Grid-connected inverters must have the capability of automatically disconnecting from the grid if the grid goes down. This is a safety feature. So, if there are workmen on the grid, there is no electricity going into the grid from this solar PV system. Here we see an inverter which would be used for a standalone system or a grid-connected system with a battery backup. The operating voltage of the two different inverters is quite different. Here we see an assembly of the standalone system with a generator. The generator is there, so if the batteries do not remain charged from the solar PV system, the generator can start automatically and run until the batteries are charged. This is strictly a grid-connected system with no battery backup. This is the most common type of system installed in a home. This is a grid-connected system that has a battery backup. If the grid goes down, the inverter will disconnect the system from the grid, and the home will then be supplied electricity stored in the batteries. Let's look at batteries, battery principles, battery types, and battery operation. Here are some common solar batteries. This gives us a cutaway view of the cells in the lead-acid battery. This is currently the most popular type of batteries used in solar PV systems. Many lead-acid batteries have caps which allow excess pressure to be relieved. This opening also allows for the water in the battery, which evaporates, to escape. These particular batteries must be serviced regularly by filling them with water. There is a special type of cap for these batteries called a recombiner cap that condenses the water vapor and allows it to return to the battery. There are sealed lead-acid batteries as shown here on slide 22. If the battery becomes too hot during charging, the pressure valve will allow water vapor to escape and reduce the battery pressure. However, if this occurs, the water is lost from the battery. It cannot be refilled. Look at battery specifications. Days of autonomy refer to the number of days the battery bank is designed to supply electricity without being charged. This would allow for that number of days with no sun on the solar panels to charge the batteries. Amp hours refers to the capacity of the battery. If it were rated, for example, at 200 amp hours, it would be able to supply 200 amps for 1 hour, or, as in the example, 100 amp for 2 hours. Batteries of these types come with recommended rates of depth of charge. There is a life expectancy, the number of cycles also associated with these batteries. Other specifications refer to environmental conditions, price, quality, and maintenance schedule. Usually the battery bank is designed for about 2 to 3 days of autonomy for non-essential systems and for 5 to 7 days of critical load systems. This is an example of battery capacity amp hours. The example shows us a 100 amp battery would supply 100 amps for 1 hour or 200 amps for 1/2 hour. We can wire two 12-volt batteries, 100 amp hour batteries, in parallel. The voltage would increase to 24 volts, but the amp hours will remain the same at 100. We can wire the batteries in parallel. In this case, the voltage will remain the same, but the amp hours would double to 200. We can also wire the batteries in series and in parallel. In this case, the 4 batteries will supply us 24 volts and a total of 200 amp hours. We see a graph of a battery state of charge ranging from 100% to less than 25%. Simultaneously, the depth of discharge will be from 0% to a little greater than 75% discharge. The amount of total energy that a battery can be obtained from a battery is a function of the rate at which the battery is discharged. The graph on slide 30 gives us different amounts of total energy with respect to different rates of discharge. This C over 500 means the battery is totally discharged in 500 hours. This C over 5 means the battery is totally discharged in 5 hours. It can be seen from the graph that the slower the battery is discharged, the more energy it has. A typical battery state of charge with respect to the seasons of the year shows a battery to be at a higher rate state of charge in the summer than in the winter. The battery charge can be measured with a hydrometer, which measures specific gravity of the fluid in the battery. The specific gravity is the fluid weight with respect to the weight of water. A specific gravity of 1.3 means the fluid weighs 1.3 times the weight of water. A fully charged battery will have a fluid-specific gravity of 1.3. The freezing point of the fluid in the battery is also a function of the state of charge. In a fully charged battery, the freezing point of the fluid will be almost minus 80 degrees centigrade. Let's do an example. The occupants of a remote home in California are designing a photovoltaic system to meet their 1,080 AC watt-hours per day requirement. They decided on a 12-volt direct current system and feel they need 2 days of autonomy and a maximum depth of discharge of 50%. They have tentatively selected a 6-volt battery with a capacity of 200 amp hours. They will maintain the battery indoors at a temperature of 77 degrees Fahrenheit. We will enter 1,080 average AC daily watt-hour load divided by 0.9, the default inverter efficiency. They will have a 12-volt system, so we divide by 12 to obtain 100 amp hours per day. Then multiply the 100 amp hour per day times 2 days of autonomy and dividing by 0.5 the desired depth of discharge, and also dividing by the battery capacity of 200 amp hours. We then determine they need 2 batteries in parallel. They have a 12-volt DC system, 6-volt batteries, so we divide 12 by 6 and determine they need 2 batteries in series. Multiplying the 2 batteries in parallel by the 2 batteries in series, we obtain and determine they need a total of 4 batteries. Let's do an example.